last 2 years. Felix was here, was talking about that. For example, last year he was giving some overview of the overall NoSQL technology and was giving a classification and a decision guide on how to map the concrete requirements of your application to the specific features of the system. And I think this is very important nowadays when we have, this is also the case with stream processing systems, we have so many systems out there, all having specific capabilities, and it's really a problem to choose the right system for the problem you have. And then, since our overall framework was about low latency and horizontal scalability, we additionally wanted some kind of support for continuous queries and corresponding real-time support, and therefore we started examining these stream processing system. What is stream processing in contrast to traditional data analytics systems that collect and periodically process huge static volumes of data? Streaming analytics systems avoid putting data at rest and process it and it becomes available, thus minimizing the time to be spent from a data item entering the system and being produced to some output. Okay? And in this context, we often talk about real-time. Oops. And when we talk about real-time, we do not really mean real-time systems. We are talking about soft real-time systems, which have a latency in a sub-second, millisecond area, but do not come with a strict upper bound of the time to respond. So, and yes, what I'm talking about today is joint research with two of my PhD students. Some of you know Felix because he was here the last 2 years. And as I told you, we are doing research in the area of NoSQL technologies. We're talking about polyglot system, looking into how we can exploit web caching for providing low latency of data provisioning, big data management, cloud data management, and other issues. And additionally, I have the privilege of being the mentor of a startup which is called Backend, and that was Felix was talking about during the last two SummerSOCs. Got to a pretty mature state, so that is now used as the product, a subject of this little startup. So you know Felix, he's the PhD student and the CEO of Backend, and the other PhD student is Wolfram Wingerrath. He mainly deals with the stream processing and real-time things, which I'm talking about today. Both of them will be finishing their PhD students during the thesis during the summer. And I'm mentioning that because also I am today talking about the stream processing systems. They are the experts. So I think I talked to Kostas. I do not know anybody else who really knows every little tiny detail of all the systems we're talking about. So if you have questions regarding the arbitrary detail of the systems, send them an email and don't ask me. Yes, and what I also wanted to mention is that I'm very happy about the two brilliant tutorials we had this morning, Kostas and Daniela, because I'm also talking about sensor data processing here in these stream processing frameworks. And I'm talking about a little bit about quality when I come to our overall framework, because, and this relates to your question this morning, because when we're talking about quality, we have to look at the overall end-to-end path. Yeah? So the quality of the backend and the NoSQL systems is very important, but the latency, the data have to spend when they are going through the web is also important. So we have to examine that as an end-to-end issue. So this is the outline of my talk, so I just want to give you some basics about scalable data processing. Then I come to the actual stream processing systems. Here I want to give you at least an overview and talk about the major properties of the systems which are out there and compare that systems to each other. And then I will talk about what we are doing with it. So we are actually focusing on providing some support for real-time databases. And The more I come to the end of the talk, the more I will be talking about our research and how these things fit into that picture. There are several papers out there. We're very happy that the overall approach, that we were successful in presenting that approach at this year's VLAB. Last year, Felix was talking about this NoSQL survey and decision guide. This is a paper which describes mainly that, what I will be talking about today. And this is the kind of exploitation of the stream processing and real-time things within our general framework. There's also a blog out there and gives you further information about this issue, and you can also learn more at the blog, which is provided by the backend startup. So what are we talking about when we talking about scalable data processing? Here you see a general data processing pipeline. Data is coming from users, for example, text or some pictures. It's coming from the web server or web server logs and from some sensors. And then it is collected at some kind of persistence or streaming layer, from where is it then pushed into some processing system which actually does the actual data processing, and then it may be served into some databases, fed in some materialized views or something, and then you can have some data center web servers which are exploiting this data. So this is the most general view to all that. Today's topic is this. Which systems are out there and which we can exploit in order to do that processing. The challenges here is the complexity of these systems. They hide complexities of scaling. Challenges are the deployment. How do we do code distribution in order to be really able to do the processing in parallel? How to do monitoring and health checks, how to assign work to nodes and processes and tasks which can run in parallel, how to balance the processing in order to make it really efficient and scalable, and how do we manage the fault tolerance, for example, if workers are going down and so forth. And currently we're talking about scaling out. That means if your load is increasing, you certainly can connect new resources to the systems in order to face this higher load. Okay, so the next step is what systems are out there. As always, there are very many systems out there who promise you to do some kind of big data processing. These are the options. In order to find out what system to use when, you can try to kind of arrange the systems along two basic dimensions, throughput and low latency. So that means that some of the systems are designed in order to reach high throughput. These are usually batch systems. Others are designed to provide a very low latency, and these are primarily the stream processing systems, the real-time systems. Yeah. And in order to be really a big data processing systems, we have to deal with some of the V's Daniela was talking about. The first one is volume. For example, we have these systems where data can be fed into some persistence layer, for example, HDFS. And then we have a batch process who is kind of processing this data, and you need kind of a unit of relevant data in order, for example, to do some aggregations or some proving or something. So you wait, store the data in the persistence layer until you have all the relevant data in order to perform some processing stuff. Okay, this is cost effective and efficient. The processing step is very efficient. And it's easy to reason about because the processing, the batch processing, for example, MapReduce is operating on complete data. But because you have to wait until you have the unit of data which is needed for processing, you have usually a high latency. Yeah? And jobs are usually performed periodically, for example, during night times. Yeah? So that has the advantage that your code can evolve, yeah? And you can then use new. If your business logic changes, you can use no code, and the overall processing principle is still valid. So the other thing is, when we talk about velocity, and we talk about real-time. Storm is a system which I will be talking a little bit more in a minute. What you have here, so you see that the data is directly pushed through the pipeline, and you immediately, as soon as some data is coming in and provided by some streaming layer, for example, Kafka, which is a queuing system, and Redis, which, as you know, is an in-memory key value store, then something is processed on the data and some information is given to the application. So the question now is, what applications have that characteristics allowing to immediately do something as soon as the data item is coming in? Yeah, because as I mentioned earlier, for some applications you need to have some kind of unit of data items to do something. So this provides a very low end-to-end latency. Yeah. And the challenges here are you have long-running jobs because you have to immediately react when some data is coming in. You actually do not have, you cannot allow any downtime to the system. Yeah. So this is a problem when your code evolves. You have an asynchronism, data may arrive delayed or out of order. Yeah. So you have no order in the arrival of data items, or it may be delayed, and you really only have that one data item in that moment when you do some processing. And that might become a problem regarding your application logic. Yes, you have incomplete input, and further issues are fault-tolerant state management and guarantees. So I was talking about clusters before the talk, and for me as a database person, it's sometimes very hard to deal with these systems because we're used to have high guarantees, like asset properties or something. Yeah? And now you really have to relax, and what we are mainly doing these days in using all these systems is to arrange trade-offs. Yeah? And that was also the topic of the tutorials this morning. Okay, and there are two architectures out there in the literature which are dealing with all these issues, and Daniela was mentioning these. The first one is the Lambda architecture. What you have here is the both combining the best of both worlds. Yeah? So you have some real-time track there, and you have some kind of batch track there. So persistence layer after the data is streamed in, and then you can do some batch, but additionally you have that real-time track where you can immediately react when some data is coming in. Yeah? So these look like this. You have a fast output via the real-time track, and you have data retention and possibly reprocessing in the batch track. Yeah? But the system has to fulfill the property of being eventually accurate, because some kind, in the logic of what you're doing on this track and this track, it has to semantically merge at the end for the application. Otherwise, it doesn't make any sense to get that information for the application, right? Yeah, typical setups here are you use, for example, Hadoop for the batch track, and Storm, which is one of the real-time systems for the real-time track, but then you have two code bases, and it's difficult to arrange and to make these two tracks probably relate to each other in a line. For this combination of systems, we have a little language which is called Hummingbird, which supports in writing applications realizing the Lambda architecture. Or you have systems like Spark and Flink, which are designed to be able to deal with both batch processing and real-time processing. This is already mentioned. The second architecture is the Kappa architecture. And this, in contrast, omits the batch layer in favor of simplicity. The basic idea is not to periodically recompute all data in the batch layer, but to do all computation in the stream processing system alone and only perform recomputation when the basic business logic changes by replaying historical data. And this is what is meant by kind of replay. So it's not a full persistence layer where you can store all the data which is coming in. It's just meant for that purpose that you can replay some short period of the let's say the news data. Yeah.
So if you think of CDP systems, you are somewhere in the middle, right? It could be that you need a window,
yeah.
and then that window may fit in the Lambda architecture on the streaming side,
right.
or so may fit here.
You will find CDP on some of the latest ones,
okay.
but actually I see them more on the side of the stream processing systems. Okay. But I will talk about something hybrid in the middle, and then we talk about so-called micro batches. But that goes later. The interesting thing here is that you only by this can implement some kind of incremental algorithm, because you need to directly react to incoming data. So the question here is, which applications do really have this property of being realized as incremental algorithms, and how many applications are out because of that? So this is a question we could possibly discuss about a little bit. Okay, quickly, typical stream operators. Filter, transform, you know that, group, aggregates, and then we have the windowing. Interesting is that you have, I think most of you are thinking about sliding windows, but you can also have tumbling windows. Yeah? So in this case, data item stays within the window for a certain period of time, and here it is already out when it's processed once. So and the question is, you will see that all these systems I will be talking about do have really very specific properties, and they have very different guarantees they give to you as an application developer. And then being asked to really map your business logic to incremental algorithms, and the next step to the specific feature of the system is really your hard task. So you really need to understand what the specific features of these systems are, and to be really prepared to program such applications. And this is why we looked into that, and this is a typical use case. I think it's the use case they use in the benchmark. It's about ad impression tracking. So we need to go into that. So in order to wrap up these basic data processing principles, we have batch processing and stream processing. We talked about that with the Lambda architecture, which provides batch and stream processing as the best of both worlds, and we have stream-only processing in the case of the Kappa architecture. And I want you to note that all the processing frameworks abstract from scaling issues. These need to be performed by some additional means. Yeah. Okay, so we come to the second part, which is the major kind, if you want to have a tutorial, because we looked into these systems and kind of compare the most popular stream processing systems to each other. So again, I first want to kind of talk about what the systems had been primarily designed for, throughput or latency. And there you have systems which are batch processing systems like Hadoop, Spark, which is kind of called the successor of kind of Hadoop or MapReduce, or others. And we have the systems which are designed to be stream processors and have this real-time capabilities. Yeah. Additionally, and this is what you possibly were asking about, is we have some kind of micro batches. So, for example, Spark, which was designed to be a batch processor, was extended by some capabilities to do some streaming. And what they do is they exploit the batch processing capabilities. They chunk the incoming streams into micro batches. This is why we have as the third group, the micro batching system. And then this is called Spark processing. And Storm is actually a native stream processor which has been extended buy some facilities to be able to process very small batches, micro batches. And now we will be talking about these systems because we think that they are the most popular ones, and we'll try to kind of compare them to each other and give you some information.
In the micro batch systems, is there a limitation on the functionality? For example, can they do any kind of windows or all kinds of windows?
I think that there's obviously a need to align things to some extent. But actually, I didn't read anything that is a real limitation. But possibly they just don't say it.
I mean, if you chunk data into batches and you have sliding windows, then obviously you have to cut windows in between, and you have somehow have to cope with the semantics.
Yeah, possibly this is a question for Wolfgang. Sorry. Okay, so let's start with Storm, which is also called Hadoop for real time. Has been developed since late 2010, was open source in September 2011 by Twitter, and eventually became an Apache top-level project in 2014. It is the first distributed stream processing system to gain traction throughout research and practice, and was initially promoted by as the Hadoop of real time because its programming model provided an abstraction for stream processing similar to the abstraction that the MapReduce paradigm provides for batch processing. Apart from being the first of its kind, Storm has also a wide user base due to its compatibility with virtually any language. On top of the Java API, Storm is also Flink compatible and comes with adapters for numerous languages such as Perl, Python, and Ruby. Storm can be run as a dedicated cluster or even as one single machine. So what you have here, what is further important on that slide, as I told you, have no primitives for joins and aggregations at all. You can only process, you have only operators to process single items, but it is very fast. Yeah? So they have a latency in the area of less than 50 or 100 milliseconds. And you see the big users are actually everywhere. Okay. What you see here is the data pipeline as it is offered by Storm. It's called topology. And it's a directed graph that represents data flow as directed edges between nodes, which again represent the individual processing steps. The nodes that ingest the data and thus initiate the data flow into the topology are called spouts, and emit tuples to the nodes downstream, which are called bowls, and these do the processing. Write the data to external storage and may send tuples further downstream for further processing.
Norbert, sorry for asking another question. What's the semantics of multiple ingoing arrows to one node? I mean, you said there is no join, so what's the semantics then?
Yeah, so it's really just the data flow that comes from your application, and that's what is possible. They don't care for. You can program it as you want. That's the message here. And in the literature, they always say that they only can support directed acyclic graphs, but you actually can create cycles. Yeah? So in the successor, which is Storm Trident, they really prohibit cycles. Yeah? So, but it's just up to you as an application programmer to relate the bowls and the spouts to each other and how to kind of map your application logic to a topology. Okay. Yes, by default, Storm distributes spouts and bowls across the nodes in the cluster in a round-robin fashion, though the scheduler is pluggable to account for scenarios in which a certain processing step has to be executed in a particular node, for example, due to hardware dependencies. The application logic is, as I told you, encapsulated in a manual definition of data flow as represented by the chosen topology. While Storm does not provide any guarantee, so what we have here is just at least once in the best case. Yeah? So it's not too much. It does provide the option of at least, yes, one processing through an acknowledgement feature that tracks the processing status of every single tuple on its way through the topology. Storm will replay a tuple if any bold involved in the processing is explicitly seen as failure or does not acknowledge successful processing. So they have an acknowledge feature. So, and when something happens, then the bold is negotiating that, and then parts of the processing can be replayed. Okay? And because they do not have any ordering at all or something, it may happen that a tuple will be processed several times. For that reason. Yeah. Okay. So actually, I've already been talking about all that. That acknowledgement feature I was talking about is what is meant here by lineage, and that means double messaging overhead, and it does not lead to really rich guarantee, as I told you. Okay, the vital parts of a Storm deployment are a zookeeper cluster for reliable coordination of the supervisors, where all the spouts and the bolts are running on as workers. In order to shield Storm deployment against and a single Nimbus server, which has the task to distribute the code of the bolts and workers over the nodes of the network. Yeah? And to restart possibly single nodes in the case of failures. Storm is scalable, fault tolerant, and even elastic. Its work may be reassigned during runtime by an input, but it does not provide any concept for keeping some state reliably or transferring it between physical nodes. The stateful applications require state management at the application level to achieve fault tolerance and elasticity. So it's just like this. They provide some in-memory technology already, which is also in-memory, but you have a remote state, and this in turn, if you really want to be real-time, this is only feasible for very small state. Okay, and yes, they, as I told you, they are pretty fast and they can provide latency in the area of less than 100 milliseconds. Okay, what they have, because they do not need some kind of, for example, a messaging system, a queuing system in between the different nodes of the system, it may happen that bolts become bottleneck. Yeah, so that tuples do queue up in front of bolts whenever data is ingested, faster than it can be processed. And this is the reason why they, in the newest version, incorporated some kind of throttling mechanism, which prevents from having too many tuples in the input of some certain bolts. Okay, in order to summarize that, you have the following properties. And important is the processing model is one at a time, so nothing like micro batches or something. The strictest guarantee is at least once. As I told you, too much, and achievable latency is significantly below 100 milliseconds. Yeah, this is poor in terms of expressiveness and guarantee, but it's very good in terms of latency and efficiency. So, and in autumn 2012, Trident was released as a high-level API with stronger ordering guarantees and more abstract, stronger guarantees. They are stateful exactly once processing, and that comes, as you can imagine, with some kind of performance penalty. They also have a more abstract programming interface with built-in support for joins, aggregations, grouping, functions, and filters. In contrast to Storm, Trident topologies are really, as I told you, really directed acyclic graphs. And this makes them less suitable for implementing iterative algorithms. Also, Trident does not work on individual tuples. This is again the micro batching thing. But on these micro batches, because currently introduces batch size as a parameter to increase throughput at the cost of latency, which however may still be as low as several milliseconds for small batches. All batches are by default processed in sequential order, one after another, although Trident can also be configured to process multiple batches in parallel. On top of Storm's scalability and elasticity, Trident provides an API for fault-tolerant state management with exactly once, processing semantics in more detail. Trident prevents data loss by using Storm's acknowledgement feature, and guarantees that every tuple is reflected only once on persistent state by maintaining additional information alongside state and by applying updates in a transaction style of processing.
And what is strong ordering in contrast to just ordering? What is strong ordering in contrast to just ordering?
They really have an order between every item which is coming in.
The two items come in the same timestamp.
Huh?
They keep the order
Okay.
writing.
Yeah. Okay.
And there are some systems where you have partitioning of the stream and then you have only ordering within a partition. Okay. And this is just an illustration of the batches and the partitioning. So you take one tuple from each partition, make it being a micro batch, and then process it. Yeah? And then it from the left to the right, one batch. But the point is, you have exactly ones, and it's a little bit slower. And you have a higher expressiveness because you have more powerful stream processing of the register. That's the difference. And that you have the micro batch. So you can process several items as a group object. Okay, the next system, which is also called real-time on top of Kafka. Kafka is an already mentioned queuing system. Samza is very similar to Storm in that it is a stream processor with a one-at-a-time processing model and at least once processing semantics. Here again we have at least private was exactly once. It was initially created at LinkedIn, submitted to the Apache incubator in July 2013, with granted top-level status in 2015. Let's see down here. Samza was co-developed with the queuing system Kafka, which is a queuing system, and therefore relies on the same messaging semantics as Kafka. Streams are partitioned, and messages, which are the data items, inside the same partition are ordered, whereas there's no order between messages of different partitions. Even though Samza can work with other queuing systems, Kafka's capabilities are effectively required to use Samza to its full potential, and therefore we assume to be deployed together, Samza to be deployed together with Kafka. Yes, I will be talking about the local state thing, which is pretty important, and they again have only single step jobs, so the overall possibilities is very single. Okay, as illustrated here, a Samza job represents one processing step in an analytics pipeline, and thus roughly corresponds to a hole in a Storm topology. In contrast to Storm, however, where data is directly sent from one node to another, output produced by a Samza job is always written back to Kafka. So we have all these Kafka layers in between.
What is then real time? I think on the slide before you said it's real time or near real time. How can something be near real time if it's based on a persistent message queue system?
Your queue has to be fast.
Yes. So they are near real time.
Guarantee that.
So this is what I mentioned at the beginning, that we are always in this context, we're always talking about software real-time.
No. What I mean is the message queuing system can deliver a message even within a day.
So you see that what they achieve is that, and this is proven by using the Kafka.
And also, you know that I worked on.
The question is the question.
No, what I said is I worked on MPCUs and it's extremely fast, but sometimes you have outlet.
There's no quality of service.
Absolutely.
Yeah.
So it
Right.
can't be
No guarantee of quality.
Yeah, Kafka gives lesser guarantees than JMS, much lesser, but it's fast. Like on this laptop, I have done 100,000 events per second.
Yeah, but you can have outreaches that last for days, right?
You can have
Messages that need the delivery which needs a day. So they don't have on average guarantees, but you can have from time to time a message that takes a long time, isn't it?
I mean, only if you wait to take it out. Because if you push it fast and take out fast, it will come fast. It's
Okay.
Obviously, they are.
Yeah.
So as you see, this Samza design decoupled individual processing steps and that eases the development of the overall application. And another advantage illustrated here is that buffering data between processing steps makes intermediate results available to other teams in the same organization, for example. And what you have here, you have a change stream of database and some front-end clicks, and then you have an enriched clicks stream which is produced by the stream processing job, and that can be used by further stream processing jobs or by different teams of the same organization having access to it. So what you see here is contrasting storm and Trident Samza is designed to handle large amounts of state in a fault-tolerant fashion by persisting state in a local database. But this local database this is what Samza does. It does not use remote state. This is always possible. From every process you can connect to a database and use it as a remote state repository. But what they do is they have a key value store, the memory key value store, which is running within the process of the workers, which can be used. And additionally, they write a changelog stream into specific partitions within Kafka. So, since Samza in this way processes messages in order and stores processing results durable after each step, it is able to prevent data loss by periodically checkpointing current progress and reprocessing all data from that point onwards in case of a failure. So if a job goes down, it just needs to do the following. It kind of needs to replay everything which is kind of stored in the changelog stream of the program. And it allows it to be stateful. So, okay, so what we have here, we have again at least once processing. We again have one at a time, but we have a better state management. So actually that's the achievement in comparison to the first achievement. Yes.
State management is still decided by the job. What does this job wants to have in the
You
state
have the
management?
possibilities to do state management
Yeah.
like this.
Yeah.
On your own.
Yes.
Yeah.
And this is but kind of
But
supported
you're
by
supported by a data structure which is highly
yes,
efficient
yeah.
and that
By
fits.
primitives
And
which
it's also, you made systems for recovery. You don't have to care about that, but you still have to define what your states are.
right.
Yeah.
Now we come to Spark, which I told you is supposed to be some kind of MapReduce successor. Spark framework is a bashing framework, actually, that is often mentioned. Yes, what is that? It offers several benefits in comparison, most notably a more concise API, resulting in comparison to the do. In less verbose application logic and significant performance improvements because they use in-memory caching in comparison to the do. In particular, iterative algorithms are accelerating the order of magnitude because data is not necessarily written to and loaded from disk between every processing step. Yes, and in addition to these performance benefits, Spark provides a variety of machine learning algorithms. As you can see, they provide such a corresponding library. Version 1 and 2. Yes, it's very successful. They have a large base of contributors, a large community, because it was already there from day one regarding Spark streaming because of the predecessor of Spark. And Spark streaming has been in development since late 2011. It became part of Spark in February 2013. Being part of the Spark framework, Spark streaming, so actually it is one single feature of the overall Spark framework now. Yes, I told you that already. Okay, so this is the important thing, because down here you see the chunking of input streams into kind of micro batches. So the core abstraction of Spark, this relates to Spark and this relates to Spark streaming. So the core abstraction of Spark are these distributed and immutable collections called RDDs, resilient distributed data sets, that can only be manipulated through deterministic operations. Spark is resilient to machine failures by keeping track of any RDD's lineage. That is the sequence of operations that created and by checkpointing RDDs that are expensive to recompute, for example, into HDFS. Spark streaming shifts Spark batch processing approach towards real-time requirements by chunking the stream of incoming data items into small batches, transforming them into RDDs and processing them as usual. It further takes care of data flow and distribution automatically. Thus, it can be made resilient to failure of any component like Storm and Samza, and further supports dynamically scaling the resources allocated for an application. Data is ingested and transformed into a sequence of RDDs, which is called a D-stream, or discretized RDD. Before being processed through the workers. All RDDs in a D-stream are processed in order, whereas data items inside an RDD are processed possibly in parallel without any order guarantees. Since there is a certain job scheduling delay when processing an RDD, batch sizes below 50 milliseconds tend to be infeasible. Accordingly, processing an RDD takes around 100 milliseconds in the best case, while close Spark streaming is designed for latency in the order of a few seconds. So, this is an example on how to use it, just an application example. What you have here is you create input stream, which is the URLs of some web pages which have been accessed within a time window of 1 second. And then you kind of do some mapping step by extracting the delivered URLs and associating them with a 1. And then you have a reduced step where for each document which has been accessed, you kind of sum up the access numbers. And this is what you do for every 1 second interval. And by this you can count the number of accesses to data items in this stream, for example. Okay, so in order to compare it to the others, it provides micro-batching as a processing model. The strictest guarantee is exactly 1, and the achievable latency is below 1 second. Yeah? So it's not as good as the others so far. Yeah. But it's more powerful, and it has exactly 1, for example. But the point actually is, I think, that it came from batch processing. It was kind of extended to be also stream or real-time capable. Yeah? So they didn't really have the choice to be as efficient as the others. Okay, the last thing is Flink. Flink, formerly known as the Stratosphere, has been developed by our friends from the Berlin Data Center. It's a project that has many parallels to Spark streaming, as it also originated from research and emphasizes the unification of batch and stream processing in the same system, so they also have both. It provides exactly once guarantees for the stream programming model and a high-level API comparable to that of Trident. Yeah, so they have pretty powerful operations for the actual processing steps. In contrast to Spark, streaming Flink does not rely on batching for stream processing internally, and thus delivers low latency in the order of Storm and Samza. Yeah, so they came from the operating system side. They designed it to be a speed processor, and that's the reason why they can be that fast. Okay, they have many libraries. This is the stream processing thing, and they also provided means for batch processing. Then we have the complex event processing. It's in their architecture. It's associated with the stream processing thing. They provide automatic backups of local state. They have RocksDB within the processes processing the data, and they allow writing save points to HDFS. They also read from the queue system as a streaming layer. And the interesting thing here, what they do is they kind of incorporate so-called barriers into the input stream. And that leads to checkpointing. And what they can do now is ordering within stream partitions. They can draw periodic checkpoints, and that helps to recovery in the case of a failure, so that they can reset a stage with checkpoint and replay the portion of data inside such a micro-batch window then again. Yeah? And that altogether allows them to guarantee exactly this.
But then they have to keep track on what they already issued out.
Right.
Yeah.
Yeah.
Which is tricky.
Yeah. And in that, they can be as fast as, for example, these two. They can have one at a time exactly once. So you see the highest guarantee these systems are able to give is exactly once. Yeah, not really.
So why is, when you go back, why is elasticity with Flink not there?
Yeah. How can you design a system in this?
So it's work in progress. I think they will be working on that, but they still did not kind of make it available for. Okay, so then you can use this kind of add impressions thing I had at the beginning and use some Yahoo benchmark, and they did that, and one result they have published, you can read more about it there, is they said Storm and Flink show sub-second latencies at relatively high throughputs, with Storm having the lowest 99th percentile